Hello everyone. Good evening. This is Gokul Alex. Welcome back to my YouTube channel. Today we are continuing our discussion on the dynamics of digital money with the focus on a topic known as Geometric Brownian Motion model, which is a very fundamental model and a basic breakthrough, blending pioneering paradigms in physics to economics. So let's look at the historic emergence of the geometric Brownian motion model. The concept of Brownian motion was proposed in early 1800, around 1820s. But in 1900, in a seminal PhD thesis, Louis Bachelier applied Brownian motion to stock prices first time. This is a landmark innovation. And in 1923, we could see that one of the pioneering physicist and mathematician who is known as the pioneer of cybernetics, Norbert Wiener, he formalized the mathematical theory of continuous random walk, where steps are normally distributed. This is one of the interesting integration to the Brownian motion architecture, where the concept of Wiener processes connecting to random walk are integrated together. And thereafter, we could see that after a span of 40 years or around so, in 1965, Paul Samuelson popularized the application of geometric Brownian motion in economics, connecting Bachelier's normal distribution to log normal, because the earlier normal distribution model is connected to, it can produce negative values, but in reality, all of us know that prices cannot go negative, right? So hence the log normal distribution was taken up. So what is the fundamental aspect of the geometric Brownian motion? It represents an asset price that grows or shrinks at a percentage rate. And like we saw in the earlier slides, it uses Wiener process component to generate random shocks to the percentage growth. So initial component is the percentage growth or the drift component, together with a volatility component or the shock component, which follows the Wiener pattern, Wiener model. So the equation can be represented textually as the percentage change in the price equals a constant drift plus a random shock provided by the Wiener process. Let's look at the mathematical model. When we look at this mathematical model, this equation can be said as the derivative of S, which equal to mu multiplied with the time increment plus the multiplication of sigma with the derivative of the Wiener process component. So as we see in this equation, mu is the drift, the constant drift we talked about, and sigma is the volatility component, and Wt is the Wiener process, the random walk component. On the right side of this slide, we see the applications of the geometric Brownian motion model. We could see that broadly, this is being applied in price projection of crypto currencies like Bitcoin and tokens like fungible tokens and non-fungible tokens and beyond. Price simulations and forecasting with an exponential, by taking this entire equation with some changes, we can see that we have taken them to the power of exponent. The prices is modeled. There are two ways in which the model can be taken. One is volatility modeling, or it could be used in risk metrics. Volatility modeling signifies when High sigma captures market swings, whereas risk metrics is when we are expecting a shortfall. So collateral risk modeling is one domain where this Brownian motion model has a huge application. Then parameter estimation. Parameter in volatility modeling, it is very important that we do the parameter estimation. The parameter estimation, the drift parameter has to be estimated from the log returns, sigma from the standard deviation. Okay. And as we see on the stablecoin side, we can use with some customizations the zero drift model, uh, where the rate of change is measured and which is measured same. We have seen there are some assumptions to be taken. For example, we have to model the liquidation probability and liquidation probability. There should be a threshold value being assumed when we look at, we know that some of the stablecoin systems like liquidity protocol has a very good relevance in here where they model the liquidation probability. And another application is for DeFi protocols, over collateralization based DeFi protocols, where the reflection principles can be applied, and protocol designs in lending and automated market makers. So what are the important properties of geometric Brownian motion? One is wherever we are modeling multiplicative returns for the rate of change in the price, or wherever we can take in a log normal distribution where the prices stay always positive. And the third application is wherever we can look at a continuous path, where there is a chance for the jumps, we will go to a model called jump-diffusion model. Constant volatility is a crucial assumption taken in a geometric Brownian model. Sigma doesn't change over the period of time. That we assume that there is a constant volatility. And Markovian property is another assumption. Future depends only on the present. Okay, but there are some limitations on the GBM, geometric Brownian motion model. That is the reason why its applicability is somewhat limited when we look at the stable coins and some of highly volatile cryptocurrencies. One is no jumps. As we mentioned previously, crypto experiences flash crashes and depeg events that the GBM cannot model. Constant volatility is a crucial assumption. That means, but when you look at crypto, we have calm periods and wild periods. So the constant volatility assumption is always not possible. And network effect. The GBM model, geometric Brownian motion model, misses Metcalfe's network effects model, and hence it is not a good model where you are modeling the network impact on the prices. And it is not aligned to reflexivity principles. Hence, it misses the self-reinforcing bubbles and crashes associated with many of the cryptocurrencies. But still, there are interesting applications of the geometric Brownian motion. Primarily, it is the first approximation model for long-term Bitcoin projections, where we have to model, even though there are some challenges with the fat tails. The another application is it can be used for Monte Carlo simulations for portfolio risk with adjustable parameters. And also, it can be used for collateral modeling in DeFi for over collateralized assets that we have mentioned previously. And then, but when you do the reality check, the geometric Brownian motion tend to have some constraints, as we mentioned here. Bitcoin's actual returns show fat tails 10x thicker than what the GBM predicted. And stablecoin depegs follow gem process, not continuous paths. Volatility clustering requires stochastic volatility models. So again, another limitation of the geometric Brownian motion model. And like we also mentioned about the Metcalfe effects and network effects, right? It requires S-curve adoption models layered on the top of GBMs. So, but why did we mention the GBM, the Geometric Brownian Motion model? Is without understanding this, we can't go to another interesting and more advanced model called jump-diffusion model, which we will be covering in the next session. Thank you so much for listening to me and following this video on Geometric Brownian Motion model. Please subscribe to the YouTube channel and share this video in your circles. And thank you so much.